Now we're going to look at some trends in the periodic table. The first one we're going to look at is the size of atoms. So how do you define atomic size? So we saw those pictures, those electron clouds. It's not really anything solid that you could measure, and besides, they're way too small for us to really get a good picture of. So there's different ways of measuring them. You can look at the covalent radius, where you look at the distance between the nuclei in a covalent bond between those two atoms, and we say, well, the radius of the bromine atom is half of that distance. The van der Waals radius is when we're looking at just a solid. These are not covalently bonded together. It's just a solid. And so the distance between the nuclei then is 2 times the radius of one of the atoms. This distance divided by 2 equals that radius. So those are going to give us slightly different numbers. And there are situations where you care about exactly how it's measured. For our class, we don't need to care about it that much. So what we're going to refer to as atomic radius is the average radius of an atom based on measuring a lot of different elements and compounds. So doing the van der Waals radius, the covalent radius, and looking at it in different compounds and just kind of coming up with an average. This is always going to be smaller than the van der Waals because this guy over here, because it does include some, the ones that are covalently bonded. And you see this, the way the picture is shown here. Here we have 2 complete circles, and here they're kind of smushed together. The covalent bond does pull them in and sort of squish the atoms together, and so the radius there is going to be smaller. If we want to know a bond length, we can estimate that by just adding the atomic radii of the 2 individual atoms. That works for covalent bonds. Ions are completely different. So there are trends in that atomic radius. And this graph looks a little bizarre. Here we're looking at the radius of the atoms in picometers as we graph atomic number. So if we look at a group such as the alkali metals, a column in the periodic table, here's lithium, sodium, potassium, rubidium, cesium. As I go down that group, the elements get larger. That makes sense. They've got more protons and more electrons. They should be bigger, right? We are adding electrons to higher principal energy levels. N is increasing, and so that valence shell gets further and further away. Here's the other side of the periodic table, group 8, and we see that there's also a trend of increasing. Now, it's not linear necessarily, but we can predict that xenon is larger than argon from its position on the periodic table. Now, things get a little weirder when you go from lithium to neon. Neon is element number 10. Lithium is number 3. Why is neon smaller? That's not what you would expect, right? You'd expect more electrons, more protons, bigger atom. But we see that it goes down as you go from one side in a period to the other. So this is period 2, 3, 4, 5, and 6. These are the transition elements, and they don't follow good patterns at all. They never follow patterns. So here we're showing periodic table with atomic radius listed. So sodium 186, magnesium 160, and it keeps going down as we go across. Argon has a radius of 98. What's going on there? Well, as we imagine growing larger and larger atoms by adding electrons, right? These electrons are all getting added in the same energy level, right? From phosphorus to argon, well, argon has 3 more electrons, but they're all in the 3p sublevel, right? So if you think about distance from the front desk, right? These guys are in the same room. It's roughly the same distance. Well, why isn't it the same size then? I think I got a picture here. There's my picture. So it has to do with shielding. Okay, so we've got the core electrons and the valence electrons. The core electrons shield the nucleus. And so the electrons on the outside don't experience the full attractive power. So here's our nucleus for lithium. We've got a positive 3 charge here, and these core electrons experience a +3 attraction. This is the valence electron. It's in the second principal level. And so these core electrons effectively block some of the charge of this. So roughly, they're blocking 2, because there are 2 of them. And so this is going to experience an effective nuclear charge of approximately +1. That's less attraction than these guys experience. The force of attraction depends on the charges. If the attraction is less, then the distance is going to be larger. So, effective nuclear charge, this is not exact, but it's a good estimate. It's the atomic number, the number of protons, minus the number of core electrons, because the core electrons shield the nucleus. Valence electrons shield a little bit, but because they're all in that same level, it's not really worth talking about. So what are the effective nuclear charges of nitrogen and argon? Well, let's do nitrogen first. What is the atomic number for nitrogen? 7. It has 7 protons. How many core electrons? So it's a little, it's got 2. So sometimes it's easier to answer the question, how many valence electrons? 5. 5 valence electrons. And then there's 7 electrons total, so 2 of them must be core electrons. So there's 2 core electrons, so we subtract that, and we get an effective nuclear charge of +5. So let's look at argon. Argon is element number 18. Argon has 18 total electrons. 8 of them are valence electrons, so there's 10 core electrons. So this is a charge of +8. Just for grins, let's do neon. Neon has 10 electrons. How many core electrons? 2. So its effective nuclear charge is +8. Nitrogen and neon, their valence electrons are in the same principal level, the second level, right? Nitrogen's valence electrons experience an effective nuclear charge of +5. Neons experience an effective nuclear charge of +8. Well, that +8 charge is going to pull those valence electrons closer to the nucleus. Does that make sense? Because that nucleus is more attractive, it pulls them in. As you go across a period, the effective nuclear charge increases, and the electrons that we're adding are in the same level, and so we get this tighter pull, and so as we go across, the atoms become smaller because the effective nuclear charge of the nucleus increases. So moving down a column, the principal quantum number of the valence electrons is increasing. Those electrons are going into higher and higher floors in the hotel, and of course they're farther away from the front desk, which would be the nucleus. We get larger orbitals, larger atomic radii. That makes sense. Moving across a period, the effective nuclear charge increases while the principal quantum number is the same. So you're putting electrons, the floors don't move, but you're putting electrons in the same floor of the hotel, but now that front desk is just more appealing to them because that effective nuclear charge is increasing. That part of the analogy just doesn't work very well. Stronger attraction. So you need to know these periodic trends. What about the transition metals? Well, here, as you go down a column, they're going to get larger, but as you're going across, it's pretty iffy. There's much less difference. They're going to be roughly the same size. What's going on here is that the valence shell is those s electrons, not the d electrons that are being added. So actually, as you go across in that transition metal series, we're adding more core electrons. And so as we're adding a proton, we're also adding a core electron. And so the effective nuclear charge is roughly the same as you go across. So just from trends, really can't predict that. Let's go back real quick to this graph. And so when we look at, here are the transition elements in the green. There's a little bit of a trend, but really not much. It kind of goes down and back up. So we're not going to worry about those. Come on. Okay. We should be able to answer questions like this. On the basis of periodic trends, choose the larger atom. No periodic table, that'd be too easy. Okay. So tin or iodine. So we need to find these on the periodic table and see where they are relative to each other. So I'm just going to draw a little piece of periodic table here. And there's tin, and there's antimony and tellurium, and here's iodine. So what does the periodic trend tell us? As we're going across, effective nuclear charge increases, and what does that do to the radius? It gets smaller. So as it's going across, iodine is smaller. It says choose the larger atom. So the larger atom would be tin. Okay? Germanium or polonium? So here's germanium, there's antimony in the middle, and polonium down here. Well, if we look at the trend going across, that would predict that polonium is smaller. But if we look at the trend going down, that predicts that polonium is larger. So it says, if possible, we can't tell for sure. So it would be okay to say, not possible, can't tell. What if it was multiple choice and you had to pick one? Which trend is probably more important? Adding in higher levels or that increased nuclear charge? I would guess with the higher levels. Polonium's valence electrons are 2 levels higher than germanium. I would guess that polonium's larger. Okay, so we have conflicting trends here, and if you have to choose, I choose the going down the column getting bigger trend. How about chromium or tungsten? So those are both transition elements. There's chromium and tungsten. Which one's bigger? The one that's down further, right? So tungsten would be bigger. So for transition elements, you're only going to be able to compare them if they're vertical. Because going across, nah, can't do it. Any questions?